In our last lecture, we were discussing about the imaging geometry, and we have already seen that given a three-dimensional point, okay, in a world coordinates, how do we get the corresponding point on the camera? That's to say that by applying the perspective transformation, how do we get the camera coordinates? And then we had also seen or studied the general case in the last class, where we had made the coordinate system for the camera and the coordinate system for the world to be different. We had considered that the camera is located at some other location, okay, whereby we had considered some translation, some angle for pans, some angle for tilt, and also some distance with respect to the gimbal center of the camera. So considering all these things, we had made a generalized expression, okay, whereby from the world coordinates we can get the camera coordinates. Now in the last class we had also seen that if we are trying to do the reverse process, that is to say from the camera coordinates, or rather given the camera coordinates, if I want to calculate the world coordinate point, we were finding a difficulty, and primarily that difficulty was because the world coordinate to the camera coordinate transformation was basically a many to one transformation, and as a result of that we were losing the depth information pertaining to the world coordinate point. Now let us see that what arrangement we can make to recover that depth information. Okay. Now we go back to our earlier discussion, okay, rather the earlier imaging geometry arrangement which we had seen. So we had a camera plate like this, and we had the XYZ coordinate system something like this. This was our XYZ coordinate system, and we had the optical center somewhere over here, and then if we had the image point over here, let us say that the image point is Pi corresponding to some object point, let us say P, and P was having a coordinate x, y, z, okay, and Pi was having a coordinate x, y with respect to this imaging plane, and we were all the time assuming that the coordinate system for small x, y, z and the coordinate system for capital X, Y, Z, let us consider that both the coordinate systems are the same. Now we once again consider the focal length to be lambda as we had considered before. So lambda is the focal length, and now if you remember correctly, the expression which we had got was something like this. Our small x, that is to say this small x for the camera coordinate, was equal to lambda capital X by lambda minus capital Z, and small y was equal to lambda y by lambda minus capital Z. Now from these two equations we get capital X equal to lambda minus capital Z into small x divided by lambda, and capital Y is equal to lambda minus capital Z multiplied by small y divided by lambda. Now from this first equation and the second equation, okay, what do we see? Our capital X is unknown, capital Y is unknown, capital Z is unknown. If somebody has supplied the camera coordinate point small x, small y, okay, and we would like to determine the three-dimensional point, the corresponding three-dimensional point P, then what we have from here is capital X unknown, capital Y unknown, capital Z unknown. So there are three unknowns and we have got two equations. So obviously we cannot solve uniquely for capital X, Y and Z. So what do we have to do now? What kind of solution should we look for? If I introduce a second camera plate, okay, let us say that at some other distance I introduce a second camera plate, and then for the same point capital P, okay, I obtain the corresponding image. Let us say now in the second photographic plate, second camera plate, the image is obtained at some other point Pi prime, and for which we assume that the corresponding coordinate is x prime, y prime. The corresponding image point in the second plate is x prime, y prime. In that case, I will be obtaining two similar equations like this. Is it correct? I will be obtaining two similar equations involving x prime, y prime and capital X, capital Y and capital Z, because capital X, capital Y and capital Z remains the same, because I am considering the same point in the three-dimensional space and just considering its images in two different plates. Okay. So now I will be obtaining how many equations? I will be obtaining 4 equations and I have got 3 unknowns. So it is possible for me to have a solution. So what I should do now is to add a second view in such a manner that I can get a solution for capital X, capital Y and capital Z. So let us consider some imaging arrangement like this. So we are considering a point P in the three-dimensional space, and here there is a camera, okay, whose focal length is equal to lambda. This camera is having a focal length equal to lambda. So this is a point in the three-dimensional space. So I am considering O to be the origin of the XYZ coordinate system for the first camera, and I am considering I to be the photographic plane of this first camera. And what I am doing is that this focal point, which I am calling as C, I am joining this capital P with the focal point C, and if I extend the ray PC, okay, the point where it intersects the photographic plane will give me the point Pi which I get, okay, that point Pi, okay, gives me the image point corresponding to the object point P for the first camera. Is that correct? Yes, please. Any questions? Okay. Let me repeat whatever I said. I have considered a photographic plate over here, okay, for the first camera, where the coordinate system is X, Y and Z, and along the Z axis I have considered the axis of the camera to be along Z axis, and I have considered a point C on the Z axis, okay, such that the distance OC gives me the focal length, or rather C is considered as the focal point for the first camera. I have considered a point P in the three-dimensional space. Now if I join point P with C and extend the ray, and if that ray intersects the plane of the first camera at the point Pi, then at the point Pi I get the image for the point P. Is it okay? Again, I have considered a second camera, and the coordinate system for that second camera is assumed to be X prime, Y prime and Z prime, and I have considered a point C prime along the Z prime axis, such that the point C prime is the focal point for the second camera. This is the plane of the second camera, and I have considered C prime to be its focal point and O prime C prime to be the focal length. Now if I consider a ray from capital P to C prime and extend that ray, the point Pi prime where it intersects the second photographic plate will give me the image of the point P for the second camera. Is that all right? So just make a note of it that for the first camera I have considered a coordinate system X, Y, Z, and for the second camera I have considered a coordinate system X prime, Y prime and Z prime.
So that means we have three coordinate systems, three different.
Okay, the question that was asked is that we have three different coordinate systems. Now we will make some simplifications because it is really difficult to deal with three different coordinate systems. Now there should be some relationship between all the three coordinate systems that I consider. So definitely this X, Y, Z coordinate system and X prime, Y prime, Z prime coordinate system, they must be somehow related. Alright. And even the world coordinate system with respect to which I am defining the point P, okay, that also will be related to the either of these two cameras coordinate systems. So definitely for the ease of our analysis, what we will finally do is to represent the world coordinate, the second camera's coordinate, everything with respect to the first camera coordinate system. Alright? So that is what we will do instead of considering three independent coordinate systems. So now let us say that the relation which I have between the coordinate system x prime y prime z prime and x y z is like this. X prime y prime z prime will be related to the x y z coordinate system in this manner. X prime y prime z prime will be the multiplication of a matrix R, okay, which is a 3 by 3 orthonormal matrix indicating rotation. So R is a 3 by 3 matrix which indicates rotation, and T is a 3 element column vector, okay. T is a 3 element column vector indicating translation. All right. So this is how x prime y prime z prime and x y z will be related to each other. And now let us assume that the coordinate of this point P with respect to the coordinate system of the first camera is small x0, small y0 and small z0. So instead of writing this as capital X, Y and Z with respect to the world coordinate, okay, I will now write the coordinate of the point P with respect to the coordinate of the first camera as x0, y0 and z0. And I am making an assumption, and that assumption is that both the cameras, that is to say the camera number 1 and camera number 2, they are having exactly identical focal length. So I am assuming that OC, the distance of OC is equal to the distance of O prime C prime, and that is equal to the focal length lambda. So mind you, my basic assumption which I am making is that both the cameras are having exactly identical focal length. All right. And x0, y0, z0 is the coordinate of the point P with respect to this coordinate system x, y, z. And I have already defined the relationship between the x prime, y prime, z prime and the x, y, z coordinate system. So now just consider this first camera, okay, and assume that the coordinate for the point Pi is xi, yi, and assume that the coordinate of the point Pi prime with respect to the x prime, y prime, z prime coordinate system is xi prime, yi prime, but with respect to the x prime, y prime, z prime coordinate system. Of course, I can convert this x prime, y prime, z prime coordinate system back into the x, y, z coordinate system. Okay. So let us first consider the first camera only, where I have got a point Pi as the image point and its coordinate is xi, yi. I know the point x0, y0, z0 in 3-dimensional space. The focal length lambda is given to us. So now what should we get as the relation between x0, y0, xi, yi and z0? I will get a relationship in terms of lambda, proceeding in the same way, okay, as we did for the imaging geometry. So that means to say, by considering the similar triangles once again, okay, we get this relation for the first camera. For camera number 1, this is my camera number 1. For the camera number 1, I get x0 by xi equal to y0 by yi, and that is equal to lambda minus z0 divided by lambda. I call this as equation number 1. All right, and for camera number 2, if I want to make the representation with respect to x prime, y prime, z prime coordinate system, okay, then I should better represent this point P with respect to the x prime, y prime, z prime coordinate system. So let us say that the coordinate of P, okay, coordinate of P with respect to x prime, y prime, z prime coordinate system is x naught prime, y naught prime, z naught prime. So the point P with respect to x, y, z was x0, y0, z0, and the same point P with respect to the x prime, y prime, z prime coordinate system is x naught prime, y naught prime, z naught prime. And considering this, again by applying the similar triangle principle for the camera number 2, okay, what do we get? We get, can anybody tell me? X naught prime by xi prime becomes equal to y naught prime divided by yi prime, and that is equal to lambda minus z naught prime divided by lambda. All right. So now this is my equation number 2. If I want to solve for the coordinate of the point P, okay, I have slight difficulty because for camera number 2 I have represented everything with respect to camera 2's coordinate system, and for camera number 1 I have referenced everything with respect to camera 1's coordinate system. So all that I have to do is a coordinate transformation, and I have already defined this relationship for the coordinate transformation. But one thing, that if I assume the coordinate systems relationships to be like this, that means to say with respect to x, y, z, the x prime, y prime, z prime coordinate system can have translation as well as a rotation, then I think we are unnecessarily considering quite a complicated imaging situation. Because after all, what do we need? We need to take the image of the point P from two distinctly different positions. So why should we consider such a kind of general case where the two cameras coordinate systems may have some rotational relationship as well as translation relationship between them? Let us consider some kind of a simplified geometrical arrangement between the two cameras such that we consider only translation, okay, no rotation. We consider only translation, and that too the translation we will consider only along one particular axis. That means to say that I am considering a relationship of this nature. X prime, y prime, z prime is equal to I being the identity matrix, x, y, z plus delta x 0, 0, or I consider the camera arrangement such that x prime, y prime, z prime is equal to identity matrix product x, y, z plus 0 del y 0, or I consider x prime, y prime, z prime equals to I product with x, y, z plus 0, 0 delta z. So I will try to consider either of these three kind of imaging arrangements. That means to say what? If this is the point, this is the plane of the first camera and this is the plane of the second camera, okay, then if this is the z-axis of the first camera and this is the z-axis of the second camera, then all that I am considering between these two cameras, that is camera number 1 and camera number 2, is a displacement by an amount delta x in the x direction. So if this is the origin for the first camera O and this is the origin O prime for the second camera, and if the distance between them is delta x, okay, and if this happens to be the z-axis for the first, this happens to be the z-axis for the second camera, then I get this delta x displacement. So in that case, I am considering my first model, model number 1, where I have assumed that along x there is a shift delta x between the two cameras, but along y there is no shift, along z there is no shift. And that is how I happen to consider the two cameras plane to be the same, because they belong to the same z. I have considered the z displacement to be 0. Or the other alternative could have been where I consider one plane over here and another plane over here, okay, this being the origin of the first camera, this being the origin of the second camera, like this, and I have a displacement by an amount delta y between the two cameras. Alright, so thereby I will be having the second model, that is a displacement delta y only in the y direction. For x and z the displacement is 0. Or I can have a third arrangement. And what is the third arrangement? I have got my x plate over here. I have got my first camera's photographic plate over here, and I have got the second camera's photographic plate somewhere over here. Alright, and this is the z-axis for the first camera and this is the z-axis for the second camera, and the two origins are just shifted from each other by an amount delta z. Okay, so that is the third arrangement which is given by this equation. Now the first one and the second one, okay, where we had considered the same plane, okay, but the cameras are just laterally displaced. So this kind of stereo camera model is called as lateral stereo geometry. Lateral means the two cameras are just laterally shifted. And the other arrangement which I had, okay, whereby I had the separation in z-axis, there what I have is, that is to say, where the shift is by an amount delta z in the z direction, my camera displacement is along the axial direction of the camera, and this is called as the axial stereo model. Alright, so we will first consider the lateral stereo geometry, where we will assume that, this model, that is to say, the two cameras are just separated by a displacement delta x. Let us now see the situation by considering this kind of an imaging geometry. So we have considered two cameras. The first one is having the coordinates x, y, z. The second having a coordinate system x prime, y prime and z prime. Their distance of separation is delta x over here. Alright. Now I consider, and I am assuming CL to be the focal point for the first camera and CR to be the focal point for the second camera. Now the first camera, which is on the left hand side, I am calling that as the left camera, and this camera which is on the right hand side I will now call as the right camera. Alright. Now I consider an image point PL on the left camera, and I join this PL, okay, with CL and extend this ray. Supposing somewhere over here I have my point P having coordinate x0, y0, z0 defined with respect to the first camera's coordinate system x, y, z. Okay. With respect to the first camera's coordinate system, it is x0, y0, z0. Now I just extend this ray with the point CR, and supposing I get the image at the point PR. Okay, I am assuming that the point PL is having coordinate XL, YL, and the point PR is having coordinate XR, YR, and this XR, YR coordinate, please make a note that the coordinates of both PL and PR I am now representing with respect to the origin of the first camera. So this XR, YR as well as XL, YL both are defined with respect to the XYZ axis. So please don't misunderstand that this XR, YR is defined with respect to x prime, y prime, z prime. It is not. XR, YR is defined with respect to XYZ only. XL, YL is defined with respect to XYZ. Even the point P, okay, defined over here is defined with respect to the XYZ coordinate system. So now for the first camera over here, what relationship do we have? Just apply the same geometrical relationship which we had deduced earlier. Can you tell me what relation do we get for the left camera? Anybody? X0 by XL, correct, is equal to Y0 by YL, and that is equal to lambda minus. Somebody was saying CLO, actually CLO corresponds to the focal length lambda. So this distance is nothing but our lambda. So this is equal to lambda minus Z0 divided by lambda. Alright, let me call this as equation number 3 now. And for the second camera, can anybody tell me the relationship for the second camera, that is to say for the right camera? Can you tell me the relationship now? You have to do the coordinate transformation, because remember that the point XR, YR, the point PR which is having coordinate XR, YR has been defined with respect to the coordinate system of the first camera. So you have to do a shift of origin. Alright, now this is taken as the positive x direction and I have moved by an amount delta x over here. So of course the delta x value that I put is negative, but considering a shift delta x between the first camera and the second camera, very simply what we are going to have is x naught plus delta x divided by xr plus delta x, and that should be equal to y naught divided by yr, because I am not considering any shift for the y, and that is equal to lambda minus z naught divided by lambda, and this is my equation number 4. So now out of this equation 3 and 4, okay, what do we see? Which are the known quantities? I will mark all the known quantities by red. Lambda is known to us. If somebody gives me the point XLYL, this will be known to us. If somebody also tells me that corresponding to this XLYL point, corresponding to the point PL on the left image, if somebody happens to tell me that what is the corresponding point for the right image XRYR, then even XRYR will be known to us, and delta x is obviously under our control because we are shifting the two cameras with respect to each other, so delta x is known to us. So out of these two equations, okay, what I have is that I have got x0, y0 and z0 as unknowns, but really speaking I have got not just two equations, but I have in fact two equations for each one of these, so that 2 plus 2 there are 4 equations and I have got 3 unknowns, and it is possible for me to find a solution. And at first let us attempt to find a solution for z0 from these equations. Let us try to solve for z0. Okay, so what do we get in the process? If you solve these two equations for z0, the ultimate expression which you get for z0 is like this. You get z0 equal to lambda plus lambda into delta x divided by xl minus xr plus delta x. Simply solve these equations, okay, and you eliminate x0 and y0 from these equations, all right, and you will get this expression. By eliminating x0 and y0 from these two equations, you will get z0 equal to lambda plus lambda multiplied by delta x divided by xl minus xr plus delta x. Now let us look at the physical significance of this equation. This is a very important and quite an interesting equation that we have got. Now here everything on the right hand side is known to us. Lambda known to us, delta x known to us, I know what is XL, I know what is XR, because somebody has given me the corresponding points PL and PR. Delta x is known to us. So I can determine the unknown depth Z0, which was originally lost for a single camera view. Now, what is the physical significance of this equation? Let us examine this term, that is to say lambda delta x divided by XL minus within bracket XR plus this, that is XL minus XR plus delta x. Can anybody tell me that what is the physical significance of these denominator term? Just try to think over it, that what is the significance of this denominator term? Again, look at the stereogeometry over here. Alright? And you have the point XL, YL over here. You have the point XR, YR over here. Okay? And what is the physical significance of XL minus XR plus delta X? Obviously, if you are considering this XR plus delta X term, all that you are considering is that, as if to say, you are translating this point PR to somewhere over here. Okay? By considering XR plus delta X, you are translating this point PR on the first camera's photographic plate, and then you are, as if to say, finding out a relative displacement between the corresponding points in the two views. Because this is having a x coordinate equal to XL, the point PL is having x coordinate equal to XL, and the translated point PR referenced on the first image's photographic plate is having a coordinate XR plus delta X. So the difference between the two is XL minus XR plus delta X. So the denominator term over here gives you what? It gives you the relative displacement. Now, can anybody quickly tell me that what is the relative displacement if the point P is situated at infinity? Yes, the correct answer is that if I consider this point P to be at infinity, then if I translate this point PR to the first camera's photographic plate, the point PR will merge with the point PL. That means to say there is absolutely no relative shift. If you are considering some object which is at infinity, at infinite depth from you, okay, and you are trying to view that object from one position over here, and then you go over to the second position to view that particular object, okay, you will find that there is no displacement that has really taken place. Whereas for the objects which are relatively near, there you will find that some displacements have taken place between the first view and the second view. So if you find over here that the unknown depth Z0, okay, becomes inversely related to the displacement between the corresponding points in the left view and the right view. If the displacement is less, the depth is increased. From this relation, it is very clear that if XL becomes equal to XR plus delta X, the denominator term becomes 0 and we get Z0 equal to infinity. Okay. Whereas if we make this XL minus XR plus delta X, the denominator term, if we make larger and larger, okay, we will get smaller depth. Or to say it in the reverse way, that for the points which are located at relatively smaller depth, for them the displacement, the relative displacement between the two views will be more. So in order to determine the unknown depth, what we have to do is we have to find out the corresponding image points PL and PR. So that is the first task for us, that we must find out that for a given point PL on the left image, what is the corresponding point PR on the right image. So this process is a process of correspondence, finding out the corresponding point, and after doing that we have to determine, we have to determine the Z0, the unknown depth, by making use of this relation. Rather, we have to measure the relative displacement. So it is the relative displacement which gives us the idea of the depth. Alright, any questions?
So the transformation XR plus XR is actually the coordinates with respect to x0, xy.
The transformation, please repeat your question again.
XR
Yes.
is with respect to XY.
XR and YR is with respect to the XYZ coordinate system, correct?
The coordinate system.
Yes.
If we transform it to X bar and Y bar axis,
Yes.
obviously there is a substitute. If we are taking the positive X axis in this reverse direction.
Yes, yes.
So if it positive origin, it is to be taken negative.
Alright, the confusion which is asked is that whether it is positive or negative, whether the relationship which I have of x0 plus delta x and xr plus delta x, whether it will be plus delta x or whether it will be minus delta x. Now I have considered this delta x to be in sign. I mean I'm not considering only the magnitude part of it. In this case, delta x has become negative with respect to this O. Delta x has become negative, so I will substitute negative values over here. So that is how I am keeping this relationship. I am maintaining this relationship. I am not considering the magnitude of delta x. If I had considered the magnitude of delta x, in that case, in this particular case, we would have got x0 minus mod of delta x. But I am not considering that. I will just substitute the negative value of delta x for this particular case because my positive x direction is along this. Okay. So this delta x which I am considering is negative. Any other questions? Any other confusions?
Why do we get this displacements?
Okay, the question that has been asked is, why do we get this displacement? Now, it is very clear from the geometry. You are considering a point from two different positions. Okay. So, you for the first one, your point of focus is over here, and for the second point, your point of focus is at some other place. Okay. The two viewing distances are differing. Now, that is why, just see, the ray which comes from point P to this point and the ray which comes from some other point, let's say we have a point P prime, the ray which comes from point P prime, okay, that will intersect the second view at some other point. So, obviously there is a relative shift. Always there is a relative shift with reference to the, with respect to the depth of the point in three-dimensional space. Alright, because the two viewing positions are different. The only case where we don't get the displacement is when the object is at infinity. When the object is at infinity, then taking the two views, okay, will not do much of a change because we will be just seeing the same image virtually. For the same, for an object which is at infinity, even if we change the viewing positions, okay, it's not going to change our displacement.
But the viewing position has been taken care of by delta x.
Correct. But just see from this relation that if I have the point z0 at infinity, then this xl becomes equal to xr plus delta x. So I don't get any shift. Any other question? All right. So I think we will consider the further aspects of stereogeometry. We will continue this discussion further in our next class. Thank you.